Hello students. So this is again a continuation part of embedded system components. The topics that I'm going to cover in this videos are embedded firmware, other components. In this other components we have reset circuit, brownout protection circuit, oscillator circuit, real-time clock, watchdog timer, and lastly topic we have is PCB and passive components. So next we'll discuss about embedded firmware.
Embedded firmware is a flash memory chip that stores specialized software running in a chip in an embedded device to control its functions. While it refers to control algorithm and or the configuration settings that an embedded system developer dumps into the code memory of the embedded system. So firmware in an embedded system fills the same purpose as a ROM, but can be updated more easily for better adaptability to conditions or interconnecting with additional equipment. While this embedded firmware is unavoidable part in an embedded system, there are various methods available for developing this embedded firmware. So in that first method is write a program in high level languages like embedded C and C++. And another method is write a program in assembly level language using instructions supported by your application's targeted processor or controllers. So when you are writing a program in high level languages like embedded C and C++, so we have to use integrated development environment, that is IDE. So this IDE contain an editor, compiler, linker, debugger, simulator, etc. These IDEs are different for different families of processors and controllers what we are going to use. So for example, like Keil Microvision 4 IDE is used for all family members of 8051 microcontroller since it contains generic 8051 compiler C51. The instruction set what we write for either a processor or controller is different, and the program written either in the methods given above in the previous slide should be converted into a processor understandable machine code before you load into the program memory. The process of converting this program written into high level, whether it might be a high level language or assembly language, so that should be converted to machine readable binary code, which we call it as hex file creation. So this hex file creation is different depending on program techniques what we have used. So that means whether you have written a program in using embedded C or C++ using an IDE, or else whether you have written a program using an assembly level language. It depends. So hex file creation varies the type, the way in which you have written the program. So if you have written the program in embedded C or C++ using an IDE, so the cross compiler included in the IDE converts it into corresponding processor controller understandable hex file. While if you have written a program in assembly language programming, the utilities supplied by the processor or controller vendors can be used to convert the source code into hex file. So also third party tools are available, so which are of free of cost for this conversion. The one who is in the embedded software field and who is a beginner, it is strongly recommended to them to use high level languages instead of using assembly level language. So writing code in high level language is much easier than writing in assembly level language. The code written in high level language is highly portable one. So with less or little modification, the same code can be run on any different processors or controllers. The only thing you need to do is, so if you are running the same code in some other processor or controller, you have to recompile the program with the required processor's IDE after replacing the include files for that particular processor. The programs written in high level languages are not developer dependent. So if any skilled programmer can just trace out the functionalities of the program by just having a looking at the program. So it becomes much more easier if the program contains necessary comments and documentation lines. So writing in high level languages, it becomes very easy to debug also, and overall system development time will be reduced to a greater extent. The embedded software development process in assembly level language is tedious and time consuming. The developer needs to know about all the instruction sets of the processor or controller, or at least he should carry an instruction set reference manual with him. A programmer using assembly level language writes the program according to his view and taste. So often he may achieve writing a program. If he is an experienced person, he may write a program through a single instruction or by 2 or 3 instruction in his own style. So the program will be highly dependent on the developer. So it is very difficult for any other second person who is trying to understand the code, even though the program which is well documented, it is very difficult for the person to understand the code. There are two types of control algorithm designed to exist in embedded firmware development. The first type of method is control algorithm development, known as infinite loop or super loop. So where the control flow runs from top to the bottom and then jumps back to the program in a conventional procedure. It is similar to writing a while loop in C. The second method deals with splitting the functions to be executed into tasks and running these tasks using a scheduler. So this is a part of a general purpose or real-time embedded systems. So next we'll know about other system components. Other system components refers to components, circuits, ICs which are necessary for proper functioning of embedded systems. So some of these circuits may be essential for proper functioning of a processor or controller and firmware executions. So for example, we have a watchdog timer, reset ICs, brownout protection ICs, etc. So we'll discuss about these examples in the next session. So these components, circuits or ICs, if any system has to work or in a proper functioning means, so there are certain controllers or SOCs where all these components, circuits and ICs are included in a single IC, and they does not require any such external components to be connected to it. So everything will be contained or fabricated within a single IC for proper functioning. So next we'll discuss about the essential circuits for proper functioning of processor or controller of the embedded systems, like reset circuit, brownout protection circuit, oscillator circuit, real-time circuits, watchdog timers. So in detail. So next we'll learn about a reset circuit in detail. The reset circuit is essential to ensure the device when it is not operating at a proper voltage level, when the device is not guaranteed to operate when during the power on condition. The reset signal brings the internal registers and different hardware systems of the processor or controller to a known state and starts the firmware execution from the reset vector. Usually reset vector will start from 00 in any processor or controller. The reset vector or the reset signal can be either active high or active low. Since the processor operation is synchronized to a clock signal, the reset pulse should be wide enough to make time for clock oscillator to stabilize before internal reset starts. The reset signal to the processor can be applied at power on through an external passive reset circuits comprising of either a capacitor or a resistor, or else we can select an standard reset IC. So for example, we have Max 810 from Maxim Delas company. So selecting this reset IC based on the type of reset signal or else depending on logic level. So which is supported by the processor or controller what we are using. So some microprocessors and controllers contain built-in internal reset circuit, while some other may require external reset circuits. So figure below illustrates a resistor capacitor based passive reset circuit for active high and low configurations. So if you want to change the pulse width or if you want to reset the pulse width, then you can adjust by changing the values of R and C value. The brownout protection circuit prevents the processor or controller from unexpected program execution behavior when the supply voltage to the processor or controller falls below a specified voltage. So it is essential mainly in battery operated power devices where greater changes of battery voltage will drop below the required threshold. The processor behavior may not be predictable if the supply voltage falls below the predicted value or recommended voltage value. It may lead to situations like data corruptions. When the operating voltage falls below the threshold, a brownout protection circuit holds the processor or controller in reset state until it rises above the threshold voltage. So main purpose of this brownout protection circuit in certain processors or controllers is to monitor the supply voltage internally. In certain processors or controllers, they doesn't integrate a built-in brownout protection circuit. So they can go for implementing using external passive circuits or supervisor ICs. So figure here shows circuit implementation using a Zener diode and a transistor for any processor or controller. So here we are taking a active low reset logic. The Zener diode and a transistor forms the heart of the circuit or main parts of the circuit. The transistor conducts only when the supply voltage VCC is greater than that of the sum of the voltage VBE and VZ, that is base to emitter voltage and Zener diode. The transistor stops conducting when the supply voltage falls below the sum of these two voltages, that is transistor base to emitter voltage and Zener diode. So we have to select this Zener diode with the required voltage for setting the low threshold value for VCC, and we can select the values of R1, R2, R3 on the basis of electrical characteristics of the transistor what we are using in the circuit. The microprocessor supervisor ICs like DS1232 from Maxim Dallas also provides this brownout protection. So next we have oscillated circuit. In any microprocessors or controllers, which is a digital device made up of digital combinational or sequential circuits. So in any processors or controllers, instruction execution takes place in synchronize with a clock signal. So usually this oscillator unit of embedded system is responsible for generating this precise clock signals. So it is same as a heart in living beings which produces heartbeats. Certain processors or controllers integrate a built-in oscillator unit, and simply it requires an external ceramic resonator or quartz crystal for producing the necessary clock signals. A quartz crystal and ceramic oscillators are almost equivalent in their operations, only they differ with their physical differences. A quartz crystal is normally mounted in a hermetically sealed metal case with two leads coming out of it. Certain devices may not contain a built-in oscillator unit. They may require an external pulses to generate and supplied externally. Quartz crystal oscillators are available in the form of ICs, and they can be used for generating these clock pulses in such cases. The speed of operation of the processor is mainly dependent on the clock frequency. So blindly we can't keep on increasing the clock frequency for increasing the speed of the execution. because the logic circuit lying inside the processor will always have an upper threshold value for maximum clock at which the system can run. Beyond this, if you keep on increasing this, the system becomes unstable and non-functional. Not only the speed of the processor or controller is dependent on the clock frequency. Other than that, the system power consumption as well as the accuracy of the program execution also depends on the clock frequency signals. The power consumption increases with increase in clock frequency. The accuracy of the crystal oscillator or ceramic resonator is normally expressed in terms of parts per million. Figure here shows the usage of quartz crystal or ceramic resonator and external oscillator chip for clock generation. Real-time clock (RTC) is a system component which is responsible for keeping track of time. RTC holds information like current time in 12 hours or 24 hours format, date, month, year, day of the week, etc., and supplies timing reference to the system. RTC is mainly intended to function even in the absence of power. RTCs are available in the form of IC from different semiconductor manufacturers like Maxim Delas, ST Microelectronics, etc. The RTC chip contains a microchip which holds the time and date related information and backup battery cell for functioning in the absence of power in a single IC package. The RTC chip is interfaced to the processor or controller of the embedded system. For operating system based embedded devices, a timing reference is essential for synchronizing the operations of the OS kernel. The RTC can interrupt the OS kernel by asserting the interrupt line for the processor or controller to which RTC interrupt line is connected. The OS kernel identifies the interrupt in the terms of interrupt request number generated by an interrupt controller. One IRQ can be assigned to the RTC interrupt and the kernel can perform necessary operations like system date, time updation, managing software timers when an RTC timer tick interrupt occurs. The RTC can be configured to interrupt the processor to predefined intervals or to interrupt the processor when the RTC register reaches to a specified value. A watchdog timer, or simply we call it as watchdog, is a hardware timer for monitoring the firmware execution and resetting the system processors or controllers when the program execution hangs up. Depending on internal implementation, this watchdog timer either it increments or decrements a free running counter with each clock pulse and generates a reset signal to reset the processor if the counter reaches 0 for a down counting watchdog or highest count value for upgoing or upcounting watchdog. If the watchdog timer is in the enable state, the firmware can write a 0 to it before starting the execution of the code, and the watchdog will start counting. So you can write 0 if the watchdog timer is upcounting watchdog timer, and there is a chance of a piece of code which is susceptible to execution hang up. If the firmware execution does not complete due to malfunctioning within the time required by the watchdog to reach the maximum count, then the counter will generate a reset pulse and this will reset the processor. If the firmware execution completes before the expiration of the watchdog timer, you can reset the count by writing a 0 to the watchdog timer register if the watchdog is an upcount timer. So in most of the processors implement watchdog as a built-in component, and they provide a separate status registers to control this watchdog timer and the watchdog timer register for writing the count value.
If the processor or a controller does not contain a built-in watchdog timer, as usual, the same to be implemented using an external watchdog timer IC circuit. The external watchdog timer uses a hardware logic for enabling and disabling, resetting the watchdog count, etc., instead of the firmware based writing to the status and watchdog timer register. The microprocessor supervisor ICDS1232 integrates a hardware watchdog timer in it. In modern types of systems running on embedded operating system, the watchdog can be implemented in such a way that it is not used when a watchdog timer timeout occurs. An interrupt is generated instead of resetting the processor. The interrupt handler for this handles the situation in an appropriate fashion. So this figure shows the implementation of an external watchdog timer based microprocessor supervisor circuit for a small scale embedded system. Printed circuit boards, that is PCB, is like a backbone for every embedded systems. After finalizing all the components and the internal connections among them, and schematic design is created, and according to the schematic the PCB has to be fabricated. The PCB acts as a platform for mounting all the necessary components as per the design requirements, and also it acts as a platform for testing the embedded firmware. Apart from the subsystems mentioned in the previous slides, passive electronic components like resistors, capacitors, diodes, etc. are also found on the board. They are mainly used for, or they work as co-workers of various chips contained in the embedded hardware, and also they are very essential for proper functioning of your embedded systems. For example, providing a regulated ripple-free supply voltage to the system, a regulator IC and a spike suppressor filter capacitors are very essential. So this ends module 3 embedded system components, and these are the two books for references.